Hey everybody! Welcome back for the next episode of Let's Be Brilliant, where we take a look at interesting problems from Brilliant.org and discuss the solution. Without further ado, here's the problem we'll be looking at this time around. Three squares of different areas are side by side. The middle square's area is 16, and its opposite sides are each collinear with an adjacent square's side. What is the area of the red quadrilateral? Alright then, if you'd like, pause the video, take a few minutes to try and work out the answer to this one. Welcome back! So what'd you think? I thought this one was actually pretty neat. Let's take a look at the solution. So what we're going to do with this weird shape is turn it into a composite figure. And what I mean by that is, we're going to start with something easy to calculate the area of, and then we're going to add and subtract similarly simple pieces until we have the desired shape. Afterwards, it's just a matter of adding and subtracting the corresponding areas, and we'll have our solution. So let's start by getting rid of our weird quadrilateral and leaving just the three squares. Squares are easy. All the sides are equal, all the angles are 90 degrees, and if you know any of the dimensions, you can find the area. As we go along, we'll be sure to keep track of the total area at the bottom of the screen. We'll start with the square on the left, and since we don't know the side length, let's just call it A, in which case the area of this square becomes A times A, or A squared. This is the first simple area that we're going to add to our total at the bottom. Similarly, we don't know the dimensions of the square on the right, so we'll call it B, and the area will be B squared, and we'll also add that to our bottom equation. Now looking at the square in the middle, we know the area is 16, and from this, we can work out that the side length must be 4. This is going to be important for us later, but let's not forget to add 16 to the total so far. So now we're ready to start subtracting some pieces off. We'll start with this triangle we have at the top that we can remove. And since this triangle shares a side with the square on the left, we know that that side has length A, but the other side we don't know directly. But if we use the side lengths of the two squares on the left, we can see that it's simply just going to be the difference between these two, or A minus 4. So putting it all together, the area of this triangle will be 1/2 times A minus 4. And if we multiply this out, we'll get 1/2 A squared minus 2A. And since we had to remove this triangle from our composite shape, we'll subtract this area from our running total at the bottom. The next triangle we'll remove is the one at the bottom. This one also has a side length of A. The other side is made up of segments from the left square and the middle square. So this makes the total length the sum of these, namely A plus 4. The area of the triangle is then 1/2 times A plus 4, which gives us an area of 1/2 A squared plus 2A. Again, this triangle was removed from our composite shape, so we'll subtract its area from the total. We have one more triangle to remove, this one over here on the right. This triangle shares a side with the far right square. The other side we need is a combination of the right square and the one in the middle, for a total length of B plus 4. Now we calculate the area as before, and we get 1/2 B squared plus 2B. And once again, we'll subtract this from the total. Lastly, in order to get the shape we desire, we need to add some area in the form of this triangle here. This triangle shares a side with the rightmost square, and as you can see, it has another side that is the difference between the sides of the middle square and the smaller one on the right. And we'll call this length 4 minus B. A final area calculation gives us 2B minus 1/2 B squared, and this time, since we had to add this triangle to our composite shape, we're going to add it to our running total. And now we have the entire expression we need to represent the area of this weird quadrilateral. All that's left to do is simplify it and see what remains. So let's get started. The first thing we're going to do is distribute all of our minus signs into the parentheses, and then we'll rewrite everything below. Now things are a little simpler, and now we're free to start combining like terms. For example, I see 3 A squared terms. We have an A squared term in the front, and then 2 minus 1/2 A squared terms. And these are all going to cancel each other out, since 1 minus a half is 0. And now we can condense things a little bit, and next we'll look at our B squared terms. Again, we have a 1b squared term here, and then 2 minus 1/2 b squared terms later on. Just like with our a squared terms, these will cancel out, and we can write things a little more simply. Now things are looking pretty clear. 2a minus 2a are going to cancel each other out, just like the minus 2b and plus 2b are going to cancel out. And now, completely simplified, we can see that all of our terms dependent on the side lengths of our indeterminate squares have gone, and all that remains is 16, which is our answer and is the area of the quadrilateral, and also the area of the square in the middle. So no matter how big or small we make the two squares on the outside, we won't affect the area of the quadrilateral in the middle. If you'd like to take a crack at this and other problems, I've put the link in the description. In my next video, we'll take a look at another way to solve this problem that demonstrates using geometry why the quadrilateral has the same area as the square in the middle. But until then, let me know what you thought of this video in the comments. I played around with the new format, so I'd really like to hear your feedback. And as always, please like and subscribe and share, that'd be great, and I'll see you all next time.